Hi everyone, welcome to another video. In the previous video we introduced the logarithmic graph as the inverse function to our regular exponential graph. So you can see in this picture that I have a graph y equals 2 to the power of x, and I have this graph in blue, y equals log to the base 2 of x. And we drew in this line of y equals x just to show that one of these is indeed a reflection of another. So a lot of the logarithms we were looking at were in the form of y equals log to some base a of x, where a is a number greater than 1. So in the previous video we introduced one of these examples. Now we're going to look in this video at just some basic transformations of functions that we've talked about numerous times before in different contexts, but we're going to apply that to the log graph. So the first thing we're going to look at is the effect of changing this base of a. Now normally when we had exponentials, so consider the graph of y equals 2 to the power of x, say we drew in a graph of y equals to 3 to the power of x. Well, we noticed in previous videos in different series, if we were to draw this, it would still pass through my intercept, but it would go up a little bit steeper, if we recall. And as our number, our base number here, got bigger and bigger and bigger, our graph would get steeper and steeper and steeper. So say we drew another one in. For example, y equals 4 to the power of x. Our thing would get quite steep. Now, let's just apply this same thing to the log graph. And we're going to look at this first through a table of values, something that we're quite familiar with, will be easy to work with. And then we're going to talk about this through the lens of what we understand about inverse functions so far. All right, so let's consider this graph of y equals to log to the base 3x. Now, in order to draw this, we don't really know what this transformation changing from 2, as we had over here, to 3 is really going to do. Some of you may guess this, but let's just assume that we don't really know. So we're going to draw up a table of values again. And we drew up this table of values by writing this thing in log form in exponential form. So we're going to make, for example, we've got our base here, we've got our power, and we've got our answer that we get, the subject. So this is going to become 3 to the power of y equals to x. So this is something that we have done before. Now, if I draw up my table of values, I have x and y. I'm just going to draw in a couple of values here. I'll start from -2. Actually, because my y thing is getting inputted here, we'll draw those down there. So we have -2, -1, 0, 1, and 2. And I'm going to work through this a little bit quicker because by now we should be comfortable with these tables of values. Substituting all of these y values into here, I'm going to get my x output basically. So this one, I'm going to get 3 to the power of -2, that's 1 over 9. 3 to the power of -1 is 1 over 3. I'm going to get 1 here, I'm going to get 3 here, and I'm going to get 9 here. So let's draw this up once again, and we're going to see something interesting happen. Now, when y equals -2, so let's say that's about down here, when y equals -2, x is going to be 1 over 9. So it's going to be a pretty small sort of fraction value here. So let's do this in, let's do it in brown. So we've got a point about here. And when x equals to -1, y equals to about 1/3, so that'll go about here. When x equals to 1, y equals to 0. when y equals to 1, x equals to 3. So when y is 1, x is 3. So that's about here. And when y equals 2, we get 9. But we probably don't have room to draw all of that. But let's actually just look at what happens. So if I join these dots in this particular way, I have my graph y equals log to the base 3 of x. Now, what do I notice? Well, I can kind of see this mirror image thing playing out once again. And the idea of these inverse functions, which we've talked about before, we can see this kind of happening in our particular graph. If we look at, for example, this part of my y equals 3 to the power of x, this guy is going to be its inverse function. Now we can see as this gets steeper past the intercept, this gets narrower. So we can see if you tilt your head over so that this line is, you're looking at it as a purely vertical line, you can see a mirror image between my brown graph and my purple graph here. They are once again mirror reflected. So we can start to think about what's going to happen as this base number a gets bigger and bigger and bigger. We're going to try this for one more, for y equals log to the base 4x. To the base 4x. We can rewrite this with a base of 4. Let's make this look a lot more like a 4. Power of y, and our x being the subject. You guys can take your time with this, but I'm just going to quickly write out these values in. You can pause and have a go on your own and then come back to me when you have a go, but I will just really quickly try to do this because we want to get through some more transformations here. So this is going to be 1 over 16, 1 over 4. We have 1 and 4. So if I were to graph this guy over here, I'm going to get something that looks like this. We're going to have the same intercept once again, but my values here are going to be slightly different. And I'm going to get something that looks, let's try that again. This is going to look kind of like this. It's just going to look a lot more shallow, I guess, from these bits that go out here. And I can see, once I draw this in, y equals log to the base 4x, I can see something happening again. If we turn our heads, we can see this idea of inverse functions again. We can see a perfect reflection along the line of y equals x of my graph here and my graph over here, this blue graph down the bottom there. So as my value a gets bigger, my base for my exponentials, as my a got bigger, my graph got steeper. It shot up quicker. As my a gets bigger for my log graph, so from 2 to 3 to 4, I can see that once it passes the intercept, it becomes shallower. So this is how the dilation transformation will affect our log graph. And remember, the dilation was just about stretching something out and making something steeper or more shallow. The same kind of things are happening with my log graph, but it's going in a way that's opposite to what's happening with all of my exponential graphs. So that's the effect of changing this value of a. So we're going to make a little note of that. We're going to make a little transformation log. So the first thing we notice is as a gets bigger, so as this pronumeral a gets bigger, my graph gets, let's say this is, I don't know, less steep. Because comparing all of these, as we go from 2 to 3 to 4 in my log graphs, I can see my graph is getting a little bit, it's not increasing at the same rate. The rate it's increasing in the y is slowing down. It's getting more shallow. So that's one of them. Now let's look at the different types of other transformations we encountered, which was, the ones we're going to be talking about in this video, is our translations. And we're going to apply a lot of similar sort of things here. If we have any graph, for example, y equals log to the base a of x, let's just draw one roughly. So let's look at what happens when we include some translations, some horizontal and vertical translations. Now, we don't know what this base a is, but I've just drawn sort of just an arbitrary graph in the general shape of a log. Now, what would happen if we wanted to sketch y equals log to the base a of x plus 1? Well, we remember that this guy over here, the thing that gets added or subtracted, this is our vertical translation. So if it's a positive number, if we're adding, our graph is going to get shifted up. If it's minusing, our graph is going to get shifted down. So what's going to happen is everything is going to get shifted up one. So this point down here, that's probably a good one to start. That will get shifted up 1 unit, and all of these things here will get shifted up 1 unit. About here, and let's say down here goes to about here. So I'm going to get a graph that looks, and the drawing's not going to be perfect, but I'm going to get a graph of my log that's shifted up by 1 unit. Now let's try one more, and in the next video, of course, we're going to have plenty of practice sketching these with multiple transformations, but we're just slowly going through them in this video. So let's try another one. Y equals log to the base a of, we'll go x plus 2. Now, what do we remember from when our transformation, our number getting added or subtracted, when it's attached to my x inside the bracket? Well, we remember this as being, when we looked at parabolas and our cubics and exponentials and all of these things, we identified that this guy, that thing was going to be a horizontal translation. So it's going to shift it left and right. When this one, the vertical is up and down, horizontal is left and right. Now, we remember here that our x plus 2, when our thing adds, we're shifting to the left. With our horizontal translations, we observed in many videos before, please watch those if this is new to you, an opposite kind of thing happening. If it was x plus 2, we shifted to the negative direction. If we were minusing, we shifted to the positive direction. Now this thing, x plus 2, means a shift 2 units to the left. So here, it's going to shift 2 units to the left. Just like this one up here went 1 unit up. So everything is going to shift. Now remember, we noticed something about these particular graphs. When we had our regular y equals log a to the x, we noticed that there was actually point where this essentially got really, really close to this line, this asymptote, but it never really touched it. So I'm just going to label this in again before we do our second transformation. We had an asymptote of at x equals to 0 here, at this line x equals to 0. So all of my log graphs so far approached it, got really, really, really close, because we notice these fractions sort of getting smaller and smaller and smaller, but they approached 0. They never actually touched it. Now, when we have this kind of horizontal translation, this shift, everything is going to get shifted 2 units to the left. So the asymptote as well is going to get shifted 2 units to the left. So instead of it being at 0, it's going to be at -2. Another pretty key sort of significant point here is my x-intercept. My x-intercept was 1, so it's going to get shifted 2 units to the left. So from +1, it's going to go to -1. That's going to be my intercept here. And basically, as we draw this, we can figure out the y-intercept as well, but we'll do that in the later video. But everything is going to get shifted along 2 units, and we'll get something sort of looking like this. It's not a very good drawing, I know, but it's the best I can do. There we go. So we have our log graph here of y equals to log to any base a x plus 2. The main takeaway here is just recapping over those main transformations that we've looked at before. Our dilation, our stretching of the graph, and our translations where we shift left and right. And they work in the same way as they did for our other functions. The only thing is we have a different key feature of our logarithm, which is this asymptote. So our asymptote is going to get shifted as well as our intercept and all of the other things when we have our vertical and horizontal translations. And with our dilation, it will happen like we saw up here. But that brings us to the end of this video. We're just introducing these. So in the next video, we'll look at some more formal practice questions in which we have to sketch these logarithmic graphs with multiple transformations.